Good afternoon, everyone. We're going to go ahead and start into our next section of chemical kinetics, and we're actually going to look at what are called rate laws, and we're going to also talk about reaction mechanisms. Now, by the end of this, you should at least have the background information to start the conversation on doing the math for finding a rate law and using the other information as such. Let's go ahead and get started. The first thing is, what is a rate law? Now, a rate law or rate equation basically gives us a quantitative relationship or a mathematical relationship between the rate of the reaction and the concentration of the reactants that we're using. The way that we find this rate law, we have to actually do experiments to find it. We actually have to go about finding this experimentally. Now, one part that's going to be very crucial is the rate law has to include all parts of the reactants from the final reaction. So I cannot have a rate law that only has one reactant in it if my reaction has three reactants. All of them have to be represented. Now, the general form that this takes is we have rate equals K, which is our rate constant. It's going to change at each temperature, times the concentration of A raised to an exponent or a power, times the concentration of B raised to an exponent power. Now, this is why we have to have it experimentally discovered or found, because depending on the type of situation, the temperature that we're at, a lot of the background information, it'll help us to figure out what's going on with our reaction order, which is what these stand for. Now, when we deal with reaction orders, we have three main ones that we're concerned about. But this is basically going to explain how the concentration affects the rate. We usually have to be specific in finding our reaction order. So we have first order, second order, and or zero order. Most people thought I was going to say third. No, it's actually zero order. Now, this is what that actually means. First, you notice we have to put it with respect to a specific reactant. So I may say, if I'm looking at this equation, yields NH3. Of course, this is unbalanced. But if I was to do this at a specific temperature, I might be able to say that it's first order with respect to hydrogen gas, or it's third order, or sorry, zero order with respect to nitrogen gas, whatever the case may be at that time. Now, what does this actually mean in terms of our understanding of what's happening in the reaction? Well, when something is first order, it means that if I change the reactant, it should affect the rate in a linear manner. What do I mean? If I double the concentration, I would expect to see that the rate also doubles. If I triple the concentration, I'd expect that it's going to triple. That would be first order. Second order would mean that it's going to actually change exponentially. So if I double the concentration, it's going to quadruple the rate. If I triple the concentration, then it's going to raise by a factor of 9 and so forth. Last but not least, if it's zero order, that means no matter how I change the actual concentration of that item, it's still not going to affect the rate. And so in the end, for a zero order reaction, the easiest way to know is they changed, they varied it, and the rate stayed exactly the same. It will be zero order with respect to that particular one. Now, once we finish finding the rate law, and we'll do some examples of this in class, we're going to find what is called the overall order of the reaction. And all that is we're going to add up those exponents that we had from finding the rate order, or the reaction order. And once we get that number, that'll be our overall order. Why do we need to know the overall order for the reaction? Well, it comes in handy when we get to this problem. We need to be able to find what K actually equals. Now, the way we're going to do this is we're going to actually plug in our experimental data that we're going to see in the other examples, and then we're going to solve for K, because K is the only thing we wouldn't know. Now, in class, we're going to look at 1991 free response 3B, and so you'll get a chance to see a little bit more how that works. But usually when you have a kinetics problem where you have to find a rate order, the next thing that they usually ask you to do is find K. Find K and find the units. So we're going to talk about that in a second. Now, the larger the K value, the faster the reaction will be. So if it's very, very small, very slow reaction. If it's a very large number, fast reaction. Now, this is crucial, and that's why I have it bolded and in red, and now I've just underlined it. The K changes with temperature. That is the only thing that will change the K. So I can change the concentrations as much as I want. It doesn't change the K value. But if I change the temperature, even 1 degree, I have to refigure all of this because now my molecules are moving at a different speed, whether up or down, however many degrees. Now, increase the temperature, increase the K, and the reaction rate. So if you want to increase the reaction rate, this is the way you have to do it. Now, the units for K will overall will usually be the reaction order minus 1. We'll talk about this more in just a second. Now, when we deal with our overall rate law, there's a basic pattern that we tend to look at. This is if we have a unimolecular compound, which we'll talk about in a second. But unimolecular basically meaning is based off of only one of the reactants forming into a product, almost like a decomposition reaction. Now, the rate law, basic rate law that we find is rate equals K, showing that there's no real difference, or it doesn't make a difference when it comes to the concentration. Now, with first order, we're noticing that now we enter in and we have the concentration of A also put into the basic pattern that we're going to find. In second order, we may have A raised to the second power, just showing how it overall is going to affect. Now, the next thing that you're noticing here, or you should notice, is we have this thing called an integrated rate law. The integrated rate law is basically just it's looking at the rate and the concentration as a function of time or against time. For a zero order reaction, this is the formula that we're actually going to utilize, where A is the regular concentration of A and AO is going to be our initial concentration. So when you see this O at the beginning, it's saying at time 0. So what did you start off with? Now, this part will be given to you, for each of these, they're given to you in your reference sheet. So you don't have to worry about memorizing them, but you do need to know how to utilize them. The main way that we actually run into our integrated rate law is graphically. So knowing that many times what they'll do is they'll give you either a set of data, or they may give you they'll give you a set of data, or they'll give you an actual graph. And it's your job using that data and using that graph to figure out which order the reaction is. Not with respect to any of the things, but just overall, what is the reaction order? The way that you're going to find that out is you'll plot them according to these things. Concentration A versus T, if it gives you a straight line, then that means that it is zero order with respect to that overall reaction. If it's first order, it's going to be the natural log of A versus time. And of course, for second order, 1 over the concentration of A versus time. Notice that all of them are looking at concentration as a function of time. Now, as we continue to go through, the other thing that we need to worry about is half-life. Now, half-life we usually talk about in nuclear chemistry when we talk about isotopes breaking down to half their concentration. In this case, we could also look graphically to figure out when each of our reactants will reach half of their original concentration. And we can make predictions based off of that information. Take your time, and you want to actually memorize this information. You'll have it in your packet, but also you want to make sure you have it committed to memory. That way you'll be able to utilize it when necessary to determine the half-life of any of the substances that we're dealing with. On that note, we're going to go ahead and stop here, and I will see you in class, and we'll get things going. Have a great evening.